obtain a tower of infinitely many fields called the descendant here. For instance, at level 1, we have one descendant. And in general, some combination of this descendant could give you another primary. So this would be the definition of null field. For instance, if you start with a primary with 0 dimension, you will find that its descendant at level 1 is itself another primary. So this would be the null field at level 1. And one can find this null field at higher level, for instance, at level R times S, by considering this primary field, VPRS here, which comes with this conformal dimension. And see, here's again the center chart. And I'm labeling the field here with a new parameter here called the momentum. And beta here is the parameter parameterizing the center chart and the momentum. So since we are in generic center chart, so beta can take a generic value. And so to obtain the null field, you act on this primary with this operator, the LR, S here. And as we have seen that, for instance, at the level 1, it's just L minus 1, and it gets more complicated as you go to higher level. And whenever this null field or null descendant here vanishes, the verbal modules would become degenerate. So in that case, I would refer to this primary field here as degenerate field. And I shall always use this VR, S here to denote the degenerate field. And so this is as complicated as the structure of Verma modules can be at generic center chart. However, if you allow the center chart to take more special value for a standard rational center chart, the structure can be much more complicated. But we are not talking about that here.
Yeah, please, a minute. So are there questions at this stage? Well, if no questions, let's just go on.
So whenever we have these degeneracies in the Verma modules, we have further constraint on the correlation function and operator product expansion due to the vanishing null vector. For instance, if we have this null vector at level 1 here, and then insert it into this 3-point function here. Therefore, the whole thing must vanish, and we obtain a constraint on this 3-point function, which is an example of the so-called BPZ equation, where BPZ stands for Below-Wang, Boyakov, and Samorochikov. And one could, of course, obtain this BPZ equation at higher order by just inserting a null vector at higher level into this kind of 3-point function, or even more general correlation function. And to see how the degeneracies constrain the operator product expansion, let us go through a simple calculation here. So we compute this equation. So this is just a 3-point function for 3 primary fields. So we compute it explicitly and obtain this result, which tells us that the 3-point function here does not vanish if and only if this VP2 is VP. And so if we recall the expression for operator product expansion, or OPE for short, between the 2 primary fields in CFT. So we obtain this expansion where the sum here, sum of all the primary in the spectrum of your CFT, and conformal invariance also require that you have all the descendants from each conformal primary here. And the coefficient C here is just the 3-point function coefficients here. So when we put this 3-point function into this OP, we are left with only one primary and its descendant here, which means that the degeneracies of this degenerate field at level 1 completely constrain the spectrum of its OSPE, and the spectrum is finite. And of course, these statements also hold for higher level degenerate field. For instance, at level 2, we obtain this simple degenerate OPE here, where I only write the primary here, and dot 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 here means the descendants of these two. And so this degenerate OPEs would come in handy when we discuss about the conformal blocks for our logarithmic representation. But first, let us see what is LogCFT and log representation are. So LogCFT are special kind of conformal field theories in which the correlation function can be logarithmic, and they appear many places in theoretical physics, for instance in critical percolation, in critical polymers, and it also has been studied quite in detail for rational center short. So in this talk, we see what happened at generic center short. And so to introduce the logarithms into our theory, the cheapest way to do so is to use the derivative with respect to conformal dimensions. For instance, we have this 3-point function of 3 primary field here, and then take a derivative with respect to delta 1. So I obtain a logarithmic dependence on position here, which led to the name logarithmic conformal field theory. And so whenever you introduce this derivative of fields into the spectrum, the dilatation generator, or L0 here, would become non-diagonalized. For instance, if we have this eigen equation, and then take a derivative with respect to delta here. So I obtain some stuff here from which you can see that L0 is no longer diagonalizable, or more precisely, they have Jordan cell structure. And when you have a derivative of order n here, you would have an n+1 rank Jordan cell. And to get a more complicated structure, we further consider the derivative of null fields. For instance, we consider the linear combination of the first derivative of null field at level 1 here, where these two terms are the only possible way of writing the first derivative of null fields with respect to their dimensions. And kappa here is the parameter which characterizes the representation for this logarithmic field. In other words, if you start with different value of kappa here, you would end up with different representation. And the coupling kappa here is defined through this equation. And the expert may recall this coupling as the so-called logarithmic coupling. And so this equation here actually defines the logarithmic field W here by itself. In other words, if you do not prefer using this derivative of fields with respect to dimensions, you may define the logarithmic field W through this equation and still obtain the same algebraic structure. And so the important thing about this derivative of null field is that the null field itself must not vanish. So let us see the structure of this representation. So we start with this logarithmic field here. Then we can arrive at two non-diagonal primary, where here's the dimension. And then you can come back at this diagonal primary, which is the null field itself. One would still find the same diagram here by just replacing 1, 1 to r, s in this way. And as we shall see soon, that the coupling kappa here can be computed explicitly whenever this logarithmic representation is constrained by degenerate fields. But now I want to first translate all this representation of Virasoro algebras into the so-called conformal blocks. So conformal blocks are bases of correlation function in conformal field theories from using the operator product expansion, or in other words, they are bases of solution to the conformal identities. And we would be interested in the case of 4-point conformal blocks here. And so let us see how to compute these 4-point conformal blocks in the case of Verma module first. So we start with this 4-point function in which all the fields here are primary, And then we use the global conformal symmetries to fix 3 of the 4 points here, as we shall always do. And then I perform the OPE between V1 and V2 here, where I shall assume that the spectrum of this OPE only contains the primary field from the Verma modules. So I obtain the expansion on the right-hand side here, where the first sum here sum over all the primary in the spectrum. And again, conformal invariants require that we have infinitely many descendants from each primary. So we have the second sum here. And the coefficients is here, again, the 3-point function coefficients, which are not fixed by conformal symmetries. However, the red term here is completely fixed by conformal symmetry. So they are the solution to the word identities. And this is what we define as the conformal blocks. F delta times F bar delta here. So the left and right moving part here actually factorizes. And we shall be referring to this F delta here as the conformal block for Verma modules because they capture all the contribution from each Verma module to this 4-point function. Or more precisely, they are in fact a function of the Verma modules. And the coefficients D here we shall refer it as structure constant, which is just a product of these two 3-point function coefficients, and they only depend on the center shot. So let us see what happened when we compute this formula here explicitly to the leading order. And of course, we are always at generic center shot in this talk. And so up to the leading order, you obtain this expression from which we could already see something interesting here. So you see that this F delta here has a pole at delta equal to the 1, 1. So this is the degenerate dimension at level 1. And this pole actually comes from the non-vanishing null descendant at level 1 in the corresponding Verma modules. And in general, one can even show that if you have a non-vanishing null vector or null descendant at level r times s in your Verma module, in the corresponding block, you would have this pole delta equal delta r comma s. And this can be seen by using the so-called Samorchikov recursion, which gives us the explicit expression for this conformal block F here. And so this is all I want to say for the conformal blocks for Verma module at the moment. We'll come back to it a bit later when we talk about the POTS model. Now I want to tell you how to compute the conformal blocks for logarithmic representation. So since we know that our logarithmic representation can be described by some derivative of fields, therefore the simplest way to arrive at their blocks is to translate this derivative of fields into blocks. So let us say that we have a 4-point function in which one of the channel field is this logarithmic field here, or more precisely this one. And then we want to translate each term here into conformal blocks. And so the first term here is just a derivative of null field. So they are derivative of primary because null field is a primary. Therefore, its corresponding block would be just a derivative of this block for Verma modules with respect to dimensions. And we can do this type of comparisons because the conformal blocks for Verma modules are in fact a linear function of Verma modules. And one can do the same thing for the second term here, where it gets more complicated because you have this non-trivial generator. And F-reg and RRS here are defined in this expansion here. So in this expansion, you expand this conformal block F around this degenerate dimensions. And so this RRS here only depends on the center shot. And F-reg here is defined by this expansion. So by its definition, it has no pole at delta equal delta r comma s. And this is why we use the word reg standing for regular. And so having this explicit expression for the conformal block for this logarithmic representation is also one of the advantage of using this derivative of fields with respect to the dimensions, because it allows us to deduce it. And what we're going to do now is to show that whenever this logarithmic block here is constrained by degenerate fields, this parameter of coupling kappa here will be taking a fixed value.
Yeah, please wait a moment. So, are there any questions for the moment? I mean, I think this is probably one of the main results. I mean, this formula for conformal blocks. So, yeah, it could be a good point if there are any questions, because it will be used in the following.
I had a general question about the beginning of this talk, because so Rongwaram, you started talking about degenerate fields.
Yes.
And it seems to me that you are making, I got a bit confused about terminology, because sometimes you were saying that some degenerate fields which are null, others which are not null, and so on. I guess.
So the question is which degenerate field are null and not null?
Yeah, but you did not explain what it means for it to be null. So this terminology is confusing.
By null, you mean it has a vanishing null vector, right?
I don't know what you mean by null. I can mean whatever I want, but what do you mean by null?
So whenever the field is called degenerate, it means that it has vanishing null vector.
Yeah, but this, for example, this equation here, I'm get confused, because there is an issue about vanishing two-point function versus the vanishing of all correlation functions. Vanishing of two-point function is just an algebraic question, but vanishing of all correlation functions is a more subtle thing. One does not imply the other.
Yes. So whenever the two-point function vanish, they are null fields.
But how do you know that high-point functions will also vanish?
I'm sorry, what do you say again?
For example, on the next page, you proceeded to compute the three-point function, and you assume that the three-point function of the null field will also vanish. How do you know that?
Because we imposed the null vector vanish.
Yeah, but we are going in circles. This would be true in a unitary theory, but in a non-unitary theory, we don't know that one implies the other.
But this is true at generic central chart, right?
No. There are examples when you have a field which is null, but actually there are some correlation functions, higher point correlation functions, which do not vanish.
Yes. I mean, okay, so let me first put it this way. So in this talk, there are two kinds of null fields. The one that make this correlation function vanish, and the one that does not. And so the one that make this correlation function vanish, they come from the degenerate Fermat modules.
I mean, I don't understand how you're going to distinguish which of the two cases is realized, because in any theory, like take ON model, take Potts model,
yes,
you can look at the spectrum, you know the center charge, you can check if the condition on the previous page is satisfied. This is trivial.
Yes.
But figuring out whether there's going to be some higher point correlation function which does not vanish, this is very non-trivial, and there is no general way to figure this out.
So the question here is how to distinguish the field with non-vanishing null descendant and vanishing null descendant, right?
Yeah, exactly. That's the question.
In general, I'm not how to say this, but at the level of conformal blocks, for instance, in this talk, we shall see soon that they have different conformal blocks. But
okay, well, let's see. Thank you.
Okay, so now we want to show that this logarithmic block would have a fixed value of kappa whenever they are constrained by degenerate fields. So let us see how to do this. So we shall consider a 4-point function in which our logarithmic blocks emerge and are constrained by degenerate fields. So let us start with we start with this degenerate OPE here. So this V1P here is degenerate, and this VPR0 here is non-degenerate. Therefore, the degeneracy of this field constrain that this OPE would have this spectrum, where all the fields in the spectrum here are non-degenerate, even if they may have degenerate dimensions. And this can be shown by using the OP associativity. And so we then put these two fields here into these 4-point functions, where the field V3 and V4 here are generic. Therefore, from this OPE, we have this S-channel decomposition, where the coefficients D here again is a structure constant, and they only depend on the single shard. And the diagram here represents the conformal blocks for Fermat modules, and they are both the left and right moving, a product of both left and right moving blocks. However, since I mentioned earlier that all these fields, they are non-degenerate. This means that if they have degenerate dimensions, they would have a non-vanishing null descendant, which would lead to the poles in the conformal blocks in this decomposition. Or more precisely, we are having poles in the conformal block at this value of momentum. So could this mean that this 4-point function here actually diverges? However, if we consider the same 4-point function, but in the T channel, so we obtain a different decomposition here, where you see that all the channel fields, they have generic dimensions, and so they have no poles, and in fact, the whole T channel is finite. So by crossing symmetry, the S channel must be finite as well. And so there must be cancellation of poles in the S channel. And in fact, this is where the logarithmic block shall emerge. So let us see how the cancellation of poles happen. So because we have the degenerate fields in the 4-point function, so the structure constant will be constrained to satisfy some sort of Schiff's equation according to Virasoro and Klibo, or more precisely this one. So when we put this relation here back to the 4-point function in the S channel, and we rewrite it this way. And so from this way, you can see that the pole from the conformal blocks here is always cancelled by the pole from the ratio of structure constant here. And the whole thing is actually finite as we expected. And so this is where we're going to define the conformal blocks for our logarithmic representation. So G minus here is this combination. And by computing it explicitly, we obtain this relation here, where you see that it's logarithmic because it has this derivative of dimensions. And they are, in fact, the blocks for our log representation. So if you compare this two here with this one here, so you see that kappa is taking a fixed value now because this block is constrained by degenerate field. And so by comparing G kappa and G minus, so we obtain this simple value of kappa, or in other words, if this logarithmic representation is constrained by this degenerate field, we would have this value of coupling. And if we had started with the other type of degenerate fields like this, we would obtain different blocks, but a slightly different value of coupling here. Or in conclusions, this logarithmic representation, they can take two fixed value of coupling whenever they are constrained by degenerate fields. And so far, we have been computing this G minus here from a very specific 4-point function here. However, the expression here for G minus is still valid, even if you change this V1P and VPR0 here to be more generic field. as long as the ratio of structure constant here are constrained by degenerate fields. For instance, in the case of the Potts model, some 4-point functions do not even have any degenerate fields, but their structure constant are constrained by degenerate field. And this is because we have degenerate fields in the spectrum of the model. And so I finished the subjects of the logarithmic blocks and logarithmic
So are these fields of the Potts model now degenerate with vanishing descendant or with non-vanishing descendant?
You mean the degenerate fields in the Potts model?
Yeah.
So the degenerate field in the Potts model has vanishing now descendant.
Well, it seems to me that there was this recent work of Zahn and Gorbenko who showed that in some cases there are non-vanishing, well, non-descendant.
Yes. So in that case, we don't. In that case, they would actually belong to the logarithmic representation. Whenever you have the fields with degenerate dimensions, but they have non-vanishing now descendant.
But this brings me back to my question. Given any field, how do you know if the null descendant is vanishing or non-vanishing? You seem to be assuming that it's going to be vanishing, but based on what?
I mean, in the assumption in this, what I have been working is that, so the null descendant vanish whenever the correlation function which has this null descendant vanishes. I mean, they give the BP-set equation which lead to this relation.
But this assumption does not hold in this theory. So we know examples where it does not hold. It has been shown that at least for some fields, it definitely doesn't hold. So how do you know when it holds and when it doesn't hold?
I mean, for instance, if you consider the 4-point conformal blocks for degenerate field, I mean, where the channel field is the degenerate field. In this case, the conformal block is always finite. But if you consider these 4-point blocks for the fields with non-vanishing, then in this case, the 4-point conformal blocks would diverge. And if you want an example for this.
No, I mean, can we go to the page, like to 2 pages up where you consider the finite OPE?
Yes.
Yeah.
You mean
here. Yeah, this equation 24.
Yes.
This equation 24 assumes that the field 1p, that its null descendant is vanishing.
Yes.
How do you know it's going to be the case?
That leads to the BP-set equation, which give this. I mean, the OPE has finitely many terms, for instance. But on the other hand, on the right-hand side, you have this.
I know how to derive this equation, assuming that the null descendant is vanishing, but perhaps it's not vanishing, and then the whole thing, the whole derivation is not true.
Right.
So, yeah, I'm basically confused about your assumptions. You did not state them very clearly.
I mean, so we assume that this field is degenerate, and it gives the BP-set equation. However, I mean, on this side, I mean, some of them may have degenerate dimension, but all of them are non-degenerate. It is clear to you?
No, it's not clear to me.
So if you look at this on the right-hand side, right, and then let us say that
I think we should just go on. It's not going to clarify. I already tried many times, but it's not working, and it's okay. I'll ask you later.
Okay. And okay, so now I finished this subject of logarithmic conformal blocks. So let us first again go to a very quick review on the Potts model. So as we know that this Potts model, there's some sort of generalization of the Ising model, in which each point on the lattice may take not only 2 value of spin, but q value of spin for the q state pot model. And one can even allow this q to be generic by using the so-called fortune clustering cluster representation. So this is a random cluster model in which the cluster are defined as the connected components on the graphs. For instance, this picture, we have 3 connected components, so we have 3 clusters. And so in this model, Q is no longer a spin, but there are just some parameters appearing in the correlation functions. So we can allow Q to be generic as long as the correlation functions are analytic. And so in the continuum limit, or at the critical temperature, this model has a scaling invariance, which means that we could use conformal field theory to describe it. And in the corresponding CFT, there would be a relation between the central shot and the value of Q here, which means that if you want to describe this critical Potts model at generic Q in 2 dimensions, you would need a 2D CFT at generic central shot. And so to demonstrate the applications of our logarithmic representation, we shall consider the object called 4-point connectivities. So these 4-point connectivities, they compute probability of 4 points belonging in some cluster. For instance, it may compute probability of 4 points belonging in the same cluster here. And so in the continuum limit, I mean, this model become a CFT. Therefore, this 4-point connectivity would just be a 4-point function or in CFT, or more precisely, this one. So we can then decompose it onto conformal blocks. And a few years ago, Jacobsen and Sackler proposed the spectra for this decomposition. Or more precisely, they proposed this 4 spectra for 4 different types of connectivities here. So however, to compute the conformal blocks in this decomposition, we need to know the representation of Virasoro algebra to which this field in the spectra belong. For instance, the proposal tells us that this V1, S0 here is a diagonal and it's a degenerate field, so it just belongs to the Verma modules. However, this information is not always given. For instance, the proposal does not tell us to which representation the non-diagonal field with integer indices belong. And one may first assume that all of them just belong to the Verma modules. And this appears not to be the case. So let us see how. So this non-diagonal field here, it has a non-vanishing null descendants. So when you try to compute the conformal blocks for Verma modules with this non-diagonal field, you will find that the block diverges due to the pole coming from this non-vanishing null descendant. So this means that this non-diagonal field here is not compatible with this conformal block F. Or more precisely, it does not belong to the Verma modules. But it could belong to a more complicated representation of Virasoro algebra. So since it has this non-vanishing null descendant here, we then propose that it could belong to our logarithmic representation by this relation. And because we have this degenerate field in the spectrum of the model, therefore, the logarithmic representation would be constrained to have this particular value of coupling. Or in conclusions, we are proposing this whenever you find this non-diagonal field with non-vanishing null descendant, we shall use our logarithmic blocks. And in the case, we just use the conformal block for Verma modules. And these are quite a non-trivial proposals. And so to validate it, we shall show that with this proposal, the 4-point connectivities are crossing symmetric as the 4-point function in CFT should be. Or in other words, we shall solve the crossing equation for this connectivity with our logarithmic block and find whether there are solutions or not. And we shall do this numerically. And so to start with, let us look at this formula for the connectivity. So we see that on the right-hand side here, we have infinitely many conformal blocks. So to compute them numerically, we need to truncate this sum such that we are left with finitely many terms. And we shall do so by imposing a bound on the conformal dimensions of all fields in this vector. Or more precisely, we are imposing this bound to all fields in this vector. So this means that we would have finitely many primary fields in this connectivity. And of course, we have finitely many structure constants. And since we are really imposing this bound to all fields, we would have finitely many descendants from each primary field. And if you recall that these conformal blocks, they are just infinite sum of this descendant. Therefore, we also have finitely many terms in each conformal blocks. So let us then consider the closing equation for the connectivity with this truncated vector. So of course, this equation here is not really exact because we are summing over the truncated vector. And it would become exact if we could push this bound to infinity. And so this equation here, in fact, gives us a linear equation for the structure constant at a particular value of central shot. The reason is that because we know how to compute all the conformal blocks here. So let us see how to do so. So we shall use the summological applications for the conformal block for Fermat modules for this F. And if we recall that the logarithmic blocks are just some complicated combination of this F, therefore this recursion would also give us the expression for our logarithmic blocks. And because we have truncated the spectre in this way, therefore this the conformal block here would be a truncated series, where this Q here is an elliptic norm in Z, and Z again is the position, and C here only depends on the single shot, and the sum here usually run to infinity if we did not truncate the spectre. And the nice thing about this recursion is that it converges very, very fast. Therefore, even if we use this truncated sum here, it will still have a very, very good precision for the numeric result, as we shall see. And so again, we are always at generic central shot. However, the central shot need to satisfy this inequality. So this is the condition for which the conformal block F here converges. However, so as a side remark, this recursion here tells us that the conformal block F can have a very complicated structure of pole at rational central shot due to the coefficient C here, but we do not have to worry about that. And so we know how to compute the blocks now. So let us see how to solve for the structure constant. So we shall follow the algorithm by Pico and Klibo and Santa Crela. So to solve this crossing equation, we first pick a value of central shot, and then we compute this crossing equation at as many different positions as the number of unknown is. Therefore, we obtain a linear system for this structure constant here, from which we can solve for them. And then we would compute the crossing equation again at the same central shot, of course, but at different set of position. So we would obtain another set of structure constant in the end. And one can repeat this as many times as one wants. However, in the end, since ideally this structure constant, they don't depend on the position. So the deviations among the structure constant from different set of position would give us the numerical error to this method. And so this would be the deviations among structure constant from different set of position. And in the end, we shall define the final structure constant as the average of structure constant from different set of position. So this would be the final formula for the 4-part connectivities. And however, to make sure that what we are doing here really makes sense, we need to check that as we increase the bound of the truncated spectre here, the deviation should become smaller. Because as you increase the bound, the truncated spectra would be getting closer to the real spectra, in which case the structure constant have no dependence on position at all. And so let us see what happens when we apply this algorithm to some example. So we compute the connectivity AAA. So this corresponds to the case where all the 4 points belonging to the same cluster. So at this value of Q, which corresponds to some complex central chart. And so we solve for the structure constant from 3 different set of positions, and then we compute the deviations and the average. And so for instance, at this value of bound for the truncated spectra, we obtain this deviation here for some structure constant. And as you increase the bound, so you add more field to the spectra and it becomes more correct. So the deviations become smaller and smaller. So we see here that as we increase the bound, the structure constant we found indeed converge to the constant value. So they are really the solution to the closing equation for this connectivity. And in general, one can even access this structure constant here at arbitrary positions by just adding more and more fields. Or in other words, I mean, the accuracy of our result here only depends on numeric artifacts. And how to see that our logarithmic blocks really matters for this solving equation, closing equation. So for instance, there's a recent work by Heath, Jacobsen, and Sachler. So these 3 people, they had already solved the closing equation for the connectivity before we did. And they obtained a very interesting result. However, the accuracy of their result is not at arbitrary positions because they were neglecting the logarithmic contributions. And in general, one may even try to solve this closing equation here with this logarithmic block, but with a wrong value of kappa. And again, one will find that this kind of arbitrary position can never be obtained. So this means that the logarithmic block with this specific value of kappa minus here are really relevant to these connectivities. Or in conclusions, I mean, our logarithmic representation with this kappa minus here indeed exists in the spectrum of the critical pots model. So let us see what happened when we compare this numeric result here to some well-known formula. So around 10 years ago, Delfino and Whitty, they proposed an analytic expressions for the 3-point function coefficients in 3-point connectivity. So this one, where C Liouville here is just the 3-point function coefficients. In Liouville theory, they're just some complicated products of epsilon function. And so we can extract this 3-point function coefficients from the 4-point connectivity in this way. Therefore, we could compare our numerical result with the analytic expressions. For instance, at this value of Q here, we obtain some number here. And so this is for analytic expressions. And from numerical bootstrap, we computed value cutoff of the truncated spectra. And you see that as we increase the bound for the truncated spectra, the more the two become coincide. And at the max equal 24 here, they coincide up to 20 digits, which means that our numerical result here again confirms this conjecture by Delfino and Whitty. And so the last thing I want to show you here is the analytic formula for the structure constant in these 4-point connectivities. So recently, Heath, Gronsel-Mielsen, Jacobsen, and Sachler, they found several analytic formulae for the structure constant in these 4-point connectivities by some computations on the lattice. For instance, these 2 here, and they're always the ratio of structure constant from different type of connectivities. And so of course, we check that our numerical result agree with all of the formulae. And using our numerical result, we were able to obtain several new formulae as well. For instance, these 3 here. But as we increase the indices, it gets very complicated. So this analytic formula here gives us a glimpse that there should be an analytic solution to these 4-point connectivities in the critical pots model. And understanding them would be the first step to arrive at such goal. But now we are not quite there yet. I mean, they are very complicated, non-factorized rational function. And so we want to now come to the conclusions. So we construct the log representation of Virasoro algebras by using derivative of fields. And we show that some of them have an applications in the critical pots model by solving the closing equation for the 4-point connectivities. And so what to do with this as a log representation in the future? So if you recall that there are two favors of this log representation, we recently found that the one that does not exist in the pots model, however, appear in the ON model. So this would be this W with kappa plus here. And this is still a work in progress. And so the most interesting question maybe, could we really solve all the 4-point function in this critical pots model analytically? I mean, this analytic formula for structure constant we found tends to give us hope, but we still leave this for the future work. And so far we have been considering this log representation at generic center chart. And now we have started to think what happened at rational center chart. And this again still a work in progress. And I'm done here.
Okay, thank you, Rongvoram, for the talk. Now, are there questions?
I have a question. So, if I remember it correctly, when this work of He, Jacobsen, and Saleur,
yes,
it was supposed to resolve, by enlarging the spectrum with respect to the spectrum in the work of Pico, Santachiara, and Ribot. They were supposed to eliminate certain divergences which could be present in the formula of Pico, Ribot, and Santachiara. Is this correct?
So you mean in the bootstrap connectivity by He, Jacobsen, and Sachler?
Yeah, so in the formula of in the original formula of
no,
Pico,
yeah, they
Santachiara,
found
and
this
Ribot.
divergence, and in the work by He, Jacobsen, and Sachler, they did not regularize the divergence; they just neglected the divergence.
Yeah, sorry, I think it's not the same type of divergence. I mean, the divergence I think Slava is thinking about is the divergence of connectivities as a function of the central charge.
Yeah.
And this one indeed was regularized by this work.
Yeah,
and the Rongvoram was talking about the divergence of 4-point functions as function of the dimension, of the channel dimension.
It's the function of dimension. But what does it mean, function of dimension?
So this divergence here.
But in any given theory, there is just one dimension. So why should this divergence be regularized?
Yeah, well, if you just take a block for 4-point connectivity and plug in the values of the dimensions that are predicted in the spectrum by Jacobsen and Saleur, well, you find infinity. So it basically does not make sense.
So can we say, just I would like to somehow assign some description to this here. Can you say that their proposal regularized some divergences, but not all of them?
Well, yeah, you could say that in a sense, yes.
Okay. Okay, thank you.
So, are there more questions? Yeah, well, if there are no more questions, I think we'll thank Rongvoram again. And let me point out that, yeah, many of us, well, at least Rongvoram and me, and also j'espère, will be at the Bootstrap program in Institut Pascal starting next week. So we can discuss there or discuss online from there for those who are interested. So thank you all.